In this lesson, we're going to take a look at the derivative as an instantaneous rate of change. Now, this is a very important application of the derivative, especially for fields like physics and engineering. Now, let's start by recalling something. The average velocity of an object is given by the distance it travels divided by how long it takes to travel that distance, or just distance divided by time. You've probably seen that before. For example, if you get in your car and you drive from your home to the mall, let's say, which is 20 miles away, and you do that in half an hour, then your average velocity during the trip is going to be distance divided by time, which in this case is going to be 20 miles divided by 1/2 hour, and 20 divided by 1/2, that simplifies, of course, as 40. And so your average velocity is going to be 40 miles per hour. Notice how the units remain as miles divided by hours, and we read that as miles per hour. So that would be your average velocity. Now, suppose that you were able to travel a constant velocity during this trip, like along a highway. So your house sits right along the highway. You get on the highway and you just travel 40 miles an hour for the entire trip. If you were to plot your distance, we'll call it S of t, from your starting location, 0, 0, now this represents the first 0 is your time, t, and the second 0 there is how far you are away from your home at time 0. So you're 0 miles from your home at time 0 to your ending point, which is 1/2 comma 20. So that 1/2 is time, half an hour, and the 20 is how far you are away from your house after half an hour, 20 miles away. So if you were to plot the line joining those 2 points, it would have this as its equation. S of t equals 40 times t. Now what this is this tells you how far you are from your starting point after time t, or as a function of time t. And its graph is just a straight line down here. Notice that S of 0 equals 0. So that tells you that at time 0, you are 0 miles from your home. You're at your starting location. S of, let's say, 1/4, that's quarter of an hour, or 15 minutes. Well, that's going to be 40 times 1/4, and that is 10. So in 1/4 of an hour, you are 10 miles from your home. So you would see that right here on the graph. Right here is 0.25. You'd go up and then over, and right there at 10 is where you would be. Also notice S of 1/2, that's 40 times 1/2, and that of course is 20. Oops. And so in half of an hour, you are 20 miles from your starting location, or you're at the mall, right? So right here, in half of an hour, you go up and over, and you are 20 miles from your starting location, right? So that point right there is your starting location on the graph, and that point right there represents your ending point. All right. Now also notice something else that's very important here. The slope of this line, the slope, which of course is your rise over run, well, the rise here is 20, right? 20 miles right there on the y-axis. And the run is 1/2. And of course that's 40, so that represents your average velocity. So if you were able to travel a constant velocity, the slope of your distance function from your starting point, the slope of that line is your average velocity. All right. Now, just some special notation here. S of t is called the position function of the object. Now, we'd like to ask this question. Of course, it's not possible to travel a constant velocity. You get in your car, you have traffic, you have stoplights. So your actual position function might actually look something like this. You get in your car, you're traveling quickly at first, then you hit some traffic and you slow down, then you speed up a little bit, and then you hit some more traffic, and then you speed up again and you reach your destination. This is a much more realistic position function. Now we might ask ourselves this. Let's say at this point right here, what is our instantaneous velocity? In other words, that might be like we look down at our speedometer, and at that instant, what do we see on our speedometer? What is our speedometer reading? Well, at this point right here, if we were to draw a tangent line right there, very, very close to that point, our position function is basically a straight line, right? So we're sort of traveling a constant velocity very close to this point in time right here. We're traveling, if we were to look very closely around this point in time, we would be traveling a relatively constant velocity. And our velocity, from our discussion here, it should be the slope of that tangent line. So in other words, our instantaneous velocity is going to be the slope of a tangent line. And how do we calculate slopes of tangent lines? We take the derivative. So we're going to see that our instantaneous velocity is going to be the derivative of our position function. So that's what we're going to look at now. Now, suppose that the position function for some object is given by s of t. So s of t represents the distance the object is from its starting location after time t. So t will have units of time, and s will have units of distance, like feet or meters or miles. Then if we look at s of t plus delta t minus s of t, that's going to be the distance that the object traveled from time t to time t plus delta t. So that's its change in position, or the distance that it traveled from t to t plus delta t. The average velocity of the object is then going to be given by the distance that it has traveled divided by the time that it took, or just s of t plus delta t minus s of t divided by delta t. That's going to be your average velocity. This is also denoted by the change in s over the change in time, and that is all distance divided by time. Now, if we let delta t approach 0, well, what we get is a derivative. We get that the limit as delta t approaches 0 of this quantity, well, that's just s prime of t. That's our derivative. And this represents the slope of the line tangent to the graph of s of t at time t. And that represents the instantaneous velocity of the object at time t. So we have a graphic down here. For example, suppose that the blue curve here is the position function for some object. Suppose that this point right here, we have a point right here on the curve at time 1, and then we move to the right delta t units, and we might be sitting like right here then, and after delta t, after a time change of delta t, the object would be located right here. So in other words, at time 1, the object would be this far from its starting point, and at time 3 the object would be this far. So then the average velocity is going to be the slope of that line right there. And so our average velocity is going to be the change in s divided by the change in time, right? And that's the slope of that line. So the slope equals our change in s divided by the change in time. And the change in s is just s of t plus delta t minus s of t. Now if we let this delta t approach 0, in other words, if we let this point on the x-axis approach 1, well, this line is going to become the tangent line right here, and the slope of that tangent line is going to represent the instantaneous velocity of the object at that point in time, at time 1. So let's see what happens there. And of course we've seen this before. Notice that as we let delta t go to 0, that line is becoming the true tangent line. So at this point in time, let me make that go back here again. For example, at this point right here, from time 1 to approximately time 3, the average velocity of our object would be about 6. And that might have units, let's see, I have units here of feet over seconds, so the average velocity would have units of feet per second, 6 feet per second. And then as we let delta t approach 0, notice that our change in position divided by our change in time becomes 2. So at this instant in time, at time 1, our object is traveling 2 feet per second. That's its instantaneous velocity. So we have this result. Given the position function s of t of an object, the object's instantaneous velocity is given by the derivative of the position function. And we denote that by v of t. So v of t equals s prime of t. That is the velocity of an object. All right. And so just a little description here of something that's going on. When you drive your car and you glance down at your speedometer, the value displayed on your speedometer is your instantaneous velocity of your car, or s prime of t. So your car's speedometer is actually sort of like doing calculus. It's taking the derivative of your position function. Now actually your speedometer cannot measure negative numbers, right? You don't have negative numbers on your speedometer. But s of t, s prime of t, could be a negative quantity. If s prime of t is negative, that means that your object is actually traveling back towards its starting location. So since your car doesn't display negative numbers, it doesn't tell you you're going negative 50 miles an hour, it's actually displaying the absolute value of s prime of t, which is also called the speed of the object instead of the velocity. Also, let's take note about units here. When we differentiate, our units change. So notice that if s of t has units of distance, such as feet, let's say, and let's suppose that t has units of time, like seconds, then ds dt will have units of feet per second. Now where do the feet per second come in? Well, when you differentiate down here, s prime of t is the limit as delta t approaches 0 of your change in position. Now notice this has units of feet. All of the s in the numerator here, they have units of feet. And then when you divide by delta t, that has units of seconds. So when you take the limit as delta t approaches 0, the units stay with you. They don't cancel each other out. And so you pick up units of feet per second. So that's how the units change when you take the derivative. Now in general, anytime you take the derivative of a function, the units associated with the derivative are always going to be the units of whatever f is representing divided by the units of whatever x is representing. Suppose now that you're standing on a platform that is s0 feet above or below ground level. So you're standing here and you throw an object either straight up or straight down with an initial velocity of v0 feet per second. Then the position function for that object is going to be given by this equation right here. Negative 16t squared plus v0 t plus s0. And this will have units of feet. So in other words, in 1 second, if you wanted to know how far or high the object is above or below ground level, in 1 second, you would plug the number 1 in for t, you'd put it here, and that would tell you how many feet above or below ground level the object is at that point in time. After 2 seconds, plug the number 2 in here for t, and it would tell you how many feet above or below ground level the object is after 2 seconds. That's our equation. Now let me just say a little bit about where this number 16 comes from. That number 16 comes from half of 32. Now, near the surface of the Earth, acceleration due to gravity is negative 32 feet per second squared, or negative 32 feet per second. Now what this means is that if you were to drop an object, just like, you're standing near a cliff and you release an object and it falls, every second its velocity will pick up an additional 32 feet per second. So each second it falls, the object will pick up an additional 32 feet per second. So that's why it has units of feet per second, or feet per second squared. So in other words, if you release an object near the surface of the Earth, after 1 second, its velocity will be negative 32 feet per second. After 2 seconds, it will pick up another 32 feet per second in its velocity, so it will be traveling negative 64 feet per second. After 3 seconds, it will pick up another 32 feet per second, so it will be traveling negative 96 feet per second. So that's what this the acceleration due to gravity near the surface of the Earth means. And in the English system, it is negative 32 feet per second, or feet per second squared. Now the 16 comes from half of 32, and we'll see later on how we can actually derive this equation. Right now we're just going to use it. Now in the metric system, this equation changes a little bit. In the metric system, our equation is negative 4.9 t squared plus v0 t plus s0 meters. Now time t is still in seconds. Now where does the negative 4.9 come from? Well, near the surface of the Earth in the metric system, acceleration is negative 9.8 meters per second squared, or negative 9.8 meters per second, and 4.9 is half of 9.8. So once again, we're not going to derive this. We'll look at it later on though. So now let's look at an example. keeping these two equations in mind. Now for the upcoming example, we're going to be working in the English system. So here we're assuming that a ball is thrown upward from a 10-foot high platform with an initial velocity of 100 feet per second. So first of all, for part A, let's find the position function of the ball. Let's find the s of t. So I'm going to put my work over here. So the s naught in this case is 10. That's the initial height of the ball that's being thrown upward. The initial velocity is 100, and that has units of feet per second. So our position function then from the previous slide, s of t, will be negative 16 t squared plus 100t plus 10. And that's it. That's our position function. Now let's take a look at a graphic illustrating what this position function really means. So we're going to come back to this slide, but let's just move to another one right here where we have the graphic. Okay, so what we have here is we have the ball is located right there. It's that little black dot. And you're throwing the ball upwards. So the ball is going to go up, it's going to come to a stop, and then it's going to come back down. So you're throwing it straight upward, and it's coming back down. Notice that the initial height here is at 10. That's 10 right there on the s-axis. And this axis is your time t. Now watch what happens. Alright, so the ball is going to get thrown upward. Now that blue curve there, this blue curve that is appearing here, that's not the path of the ball. The black dot is the ball. It's going straight upward. This is merely the s of t function. So notice that if I continue throwing the ball upward, after about 1 second, can't get it right on it, but after 1 second, the ball is about 96 feet in the air. So that is 96 right there. And then if we keep going, you see eventually the ball reaches its maximum height right about here. Now notice something unusual about the s of t curve at this point. At this point right here, you have a horizontal tangent line. In other words, at this point, after about 3.2 seconds or so, s prime of 3.2 is 0. Now what does that mean? Well, that means that the velocity, this s prime, remember, is the velocity. So after 3.2 seconds, the ball comes to a stop. It's reached its maximum height. It's gone up, it stops for an instant, and then it comes back down. And so that makes sense that we should have a horizontal tangent line to the graph of our position function. And then the ball comes back, starts to come back down, and it falls down until it hits the ground. So it looks like it hits the ground after about 6.3 or so seconds. Alright, so that's graphically what's going on. Just keep in mind that this blue curve is not the path of the ball. The path of the ball, it just goes up and comes back down. This is just a graph of the s of t function. Alright, now let's go back to our other slide. So now let's answer part B. So let's find the height of the ball after 1 second. Well, that's simply going to be s of 1. And we just have to put 1 in here for t, so that's going to be negative 16 times 1 squared plus 100 times 1 plus 10. And so that's going to be 110 minus 16, or 94 feet. So that's how high the ball is above the ground level at that point in time. after 1 second. Now part C, let's find the average velocity of the ball from time 1 to time 1.5. Alright, so our average velocity, well, that's going to be s of 1.5 minus s of 1 divided by 1.5 minus 1, or just half a second. So the top here, this is the distance that the ball travels from 1 to 1.5 seconds, and the bottom is the time it takes, just half a second. Now, if we evaluate s of 1.5, put 1.5 in here for t, you're going to get 124. If you put 1 in here, you're going to get 94, and then divided by half a second. So that's going to be 30 divided by 0.5, and that's going to be 60 feet per second. Feet per second. All right, so that's our answer to part C. Part D, find the instantaneous velocity at time 1. All right, well, our instantaneous velocity is v of t. That's s prime of t. So in this case, it's going to be negative 32 t plus 100. That's just the derivative of our position function up here. And now we have to evaluate v of 1, or s prime of 1. And of course, that's just going to be negative 32 plus 100, or 64 feet per second. So that's our instantaneous velocity at time 1. Now it makes sense that this number is a little bit bigger than this number, than 60, because the ball is still going upward at the 1 second mark. It's going up, and then it's coming straight back down. So at the 1 second mark, it's still going up, but it's slowing down. So at the 1 second mark, it's traveling 64 feet per second, but then it's slowing down. So its average velocity is going to be a little bit less than its instantaneous velocity at time 1. So that makes sense. Now let's see, part E, let's find the maximum height attained by the ball. Right, well, the ball will attain its maximum height when the velocity is equal to 0. So the maximum height is attained when s prime, or v, is equal to 0. All right, so we need to set s prime equal to 0. Equal to 0. And when we solve that for t, we get t is 100 divided by 32, and that's equal to 3.125. Alright, so then what we have to do to find its maximum height, we just have to evaluate s of 3.125. So the maximum height will be s of 3.125, and that is equal to 166.25 feet. Alright, so that's the maximum height attained by the ball. And remember, this 166.25 is obtained by just putting 3.125 into our s function for t. Just put it right there for t, and right there, and you'll get 166.25. Finally, let's do part F. Let's find the velocity when the ball hits the ground. Alright, I'm going to need to make a little more room here. Now, when the ball hits the ground, our position function is going to be 0. So we need to first find when s of t is equal to 0. So we need to solve negative 16 t squared Okay, so we need to solve that equation for t, and that'll tell us how long it takes for the ball to hit the ground. Now for that one, this doesn't factor very nicely, so we're going to have to use the quadratic formula. So t is going to equal negative b plus and minus the square root of b squared minus 4 times negative 16 times 10. And then all of that divided by 2 times negative 16. Now, when you solve this equation for t, you're going to get 6.35 approximately and negative 0.098. Now the negative 0.098 comes from the ball actually sort of going backwards in time. Remember, you're throwing the ball upward, and if it were to actually go backwards in time, it would hit the ground. So this one we can throw away. That's just an extraneous solution. So this is how long it will take the ball to go up from our 10-foot high platform, come to a stop, reach its maximum height, and then come back down and hit the ground 10 feet below the ball's starting position. So it'll take 6.35 seconds approximately to do that. So the velocity of the ball when it hits the ground, then we need to take this 6.35 and plug it into our velocity function. So the velocity at 6.35 will be negative 32. And just solving that, we get negative 103.2, negative 100, about negative 103 feet per second. Now the negative occurs because the ball is coming downward. It's coming back towards your starting position. When the ball's going away from your starting position, you have a positive velocity. When it's coming back towards you, it has a negative velocity. It's also a little bit bigger than 100, notice, because you were standing on the 10-foot high platform and you threw it upward with an initial velocity of 100. So it's going to go up and then come back down. If it were to come back down and land on your platform, right then it would have a velocity of 100, negative 100. But it continues a little bit further, and so it picks up a little bit more velocity, so that's why it's 103. So that makes sense. We're also ignoring air resistance here, keep in mind. There's no air resistance at all taken into account for this problem, which of course is a little unrealistic, but we're not worrying about that right now. Alright, so that takes care of this example, and we're going to look at one more. In this problem, we have a ball that is thrown upward from the base of the Washington Monument, which is 555 feet tall. And we want to find the minimum initial velocity needed for the ball to reach the top. And we want to find the velocity in units of feet per second and also miles per hour, just to put it in perspective. So our position function, remember, is given by. Now in this case, we're going to assume that S0 is equal to 0. We're going to assume that this is 0 because it says it's thrown upward from the base of the Washington Monument. And if we were standing at the bottom of the monument and threw it upward, well, our arm might be maybe 5 or 6 feet above ground level, but that's pretty small in comparison to 555. So we'll assume it's ground level, so the initial position is 0. And so this is equal to. Now, what we need to solve for is we need to find this initial velocity somehow. So that's what we need to solve. Now, let's also notice that our velocity is the derivative of our position function. So that's going to be. Now, let's note that if the ball is thrown upward, straight upward. It goes up to the top of the monument, stops for just an instant, and then falls back down. Goes in this direction. Right at the top, its velocity is 0 just for an instant. So right here, v of t is equal to 0 at this instant right here. So let's set this equal to 0, and we'll solve this for time t, and that'll tell us how long it takes to get to the top. So if we set this equal to 0 then, and we solve for t, we get 32t equals v naught, just moving the negative 32 over, or t equals v naught divided by 32. Now what we're going to do is we're going to put this into our position function up here, set this equal to 555, and try to solve for v naught. So now then, s of, so that will equal so there we put this quantity v naught divided by 32 in for the t here and over here, and this is what we get. Notice here we get a v naught squared over 32, because v naught times v naught over 32 gets us this. And now we're going to set this equal to 555, and we're going to solve for v naught now in this equation right here. So let's take this and factor out a v naught squared. So we're going to get v0 squared, v naught squared, times, and we're going to have left in here there we go. And now we're just going to take this quantity right here, all of this, divide it under the 555, and then we'll take the square root of everything to get rid of that square. And when we do that, we end up with this for v naught. And then we have to take the square root of everything. And if you evaluate that quantity on your calculator, remember to use parentheses very carefully when you do that, you will get 188.47 approximately. And that's in units of feet per second. Alright, so that answers our question, but now we want to convert this into miles per hour just to give some context to the problem. It's a little easier for people to understand how fast something is traveling in miles per hour generally than feet per second. So to do that, we have to replace the feet with miles, the seconds with hours, and then that'll convert everything. Now when you do that, remember that 5,280 feet equals 1 mile, or 1 foot equals 1 over 5,280 miles. And there are 3,600 seconds in 1 hour. Let's write that like this. All right. Remember, there are 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. So 1 second equals 1 over 3,600th of an hour. And so we just have to replace the ft with 1 over 5,280, the s with 1 over 3,600, and then simplify. So this is equal to 188.47 times 1 over 5,280 divided by 1 over 3,600, and that simplifies to and that's equal to 128 0.5 approximately miles per hour. Keeping in mind this 1 over 5 to 80, that's in miles, and the 1 over 3,600 is hours. And so that's how fast the ball would have to be thrown from the base of the Washington Monument. That is just beyond the realm of human possibility or capability. Major league pitchers can throw fastballs at most about 100, 102, 103 miles an hour is the record, somewhere in that range. And so that's just beyond the range of human capability. And so that concludes this lesson on the derivative as an instantaneous rate of change.